Welcome to the 9th lecture in the series. Today, in the last class we are talking about several types of two dimensional flows, and the last flow we considered is the source and sinks. What happens in case of a source? In case of a source, we have seen that the fluid emerges out from a point, and there we have seen that the at far distance when the radius becomes very large, there is no flow, whereas on the other hand, if you say that what happens near the when we are the radius becomes very small, when the radius becomes small, that means r tends to 0, we see that fluid speed will be extremely large, infinitely large. On the other hand, and here the flow is always in the radially outer direction, and it is symmetric, it goes out in a symmetric manner. On the other hand, if you look at a sink, here the fluid, it will absorb all the fluid and again it receives them in a radial direction. So, that is the basic characteristics of a source and then that of a sink. Now, we will understand various flows. In this part of the lecture, first we will analyze simple flows and then see what will happen if there is a source or a sink inside the flow, how this flow will be disturbed due to the presence of sources and sinks, whether the flow pattern will remain same or there will be a different pattern, because we have seen that. So, the sources and sinks are the kind of singularities enters to the flow pattern. So, when we it is expected that the flow behavior will change. Let us in this lecture we will highlight some of the examples where there are two types of flows when combined together and what is the new flow that is developed, and particularly we will think of flows which are regular and also flow which are of singular nature. Another point we have seen the two flows, one is the source, the other is the basically vortex, but what I will say that vortex flow, vortex motion. So, we have seen that in case of a particularly in case of a circulation, in the case of a source our flow is always in the radial direction, but what happens in case of a circulation? So, I will come to that in detail in this course. So, we know that in case of a vortex, the flow is always, in case of a vortex our W was I k by 2 pi log z. On the other hand, in case of a source, we have seen W is m log z. Just look at this. In the first case, the flow is in the tangential direction, particularly it is in the tangential direction. On the other hand, flow is tangential, rather in this case it is radial. So, see just look at this, here this I, how it is affecting, how the flow patterns is changing just because of this imaginary number, but both are very complex in nature and some kind of flow singularity, because at z is equal to 0 we have seen that here it is log z, here it is log z, but only because of these constants the flow pattern is changing. That is basic one of the basic difference. Here it is tangential, where here it is radial, whether it is a source or a sink. In case of a vortex and in case of a source. So, these two are very flows which are looks very symmetric, similar in nature, but only because of this constant here, this is a real number, this becomes I as a become imaginary quantity. So, because of this flow characteristics changes. Now with this I will now go to a different type of flow, particularly this is another very interesting example like flow, because we have talked about singular uniform flow, and once we have talked about uniform flow, and also in the last class just in the as an application of the Bernoulli's equation, we already know that flow past a cylinder, uniform flow past a cylinder. Let us analyze the same problem in the context of a complex velocity potential. Now let me look at Wz as uz plus u a square by z. If uz is Wz is uz plus u a square by z, and instead of uz I call this as u naught z plus u naught a square by z. Then what will happen Wz if z is equal to r e to the power I theta, then Wz equal to u r e to the power I theta plus a square by r into minus I theta, and this also I can write it as u I can always write it as r cos theta plus I r sin theta plus a square by r cos theta minus a square by r sin theta I, and this gives me, which implies I will get my phi, because W is nothing but phi plus I psi. If I equate the real and imaginary part, so I will get phi is u r u times r cos theta, then plus a square by r cos theta again. So I can call this as u r cos theta into 1 plus u r cos theta into 1 plus a square by r. In a similar manner, I can easily get psi as u r sin theta 1 minus a square by r. It is r square. There must be a r square here. So this is the velocity potential. This is the stream function. Now, which also can be written as the phi also can be written as u x, because x is r cos theta 1 plus a square by r square, and so as r tends to infinity, my phi becomes u x, and which implies my phi x is equal to u, and phi x is u means velocity in the x direction in the Cartesian coordinate. And once phi x is u, that means there is a uniform flow that represents a uniform flow along x axis. In the x direction. Now what will happen to dw by dz? If you look at dw by dz, it will be u naught into 1 minus a square by z square, and at z is equal to, what will happen to at z is equal to plus minus a. If z is equal to plus minus a, from here itself we can get it dw by dz is 0. So that means the points z is equal to a and minus a, they are stagnation point. They are called stagnation. And again, if you look at in a different manner, if z is equal to r, suppose z is a e to the power I theta. If z is a e to the power I theta, what will happen to dw by dz? This will be u naught 1 minus a square by a square e to the minus 2 y theta, which I can always write it as, because this will be 1, so that will give me e to the power I theta e to the minus I theta into u naught. So I will have e to the power I theta minus e to the minus I theta, and that will give me 2y cos theta plus I sin theta cos theta minus I sin theta. So 2y u naught e to the minus I theta into sin theta. So again, if I will say dw bar by dz bar, then that will give me minus 2y u e to the power I theta into sin theta, and from these two, this is my dw by dz. So my q, if I multiply these two, that will give a q square, that will give you 4 u naught square into sin square theta, and which gives q is equal to 2 u sin theta. That means if I have a cylinder, on the boundary of the cylinder q is, if I have a cylinder of circle of radius or a cylinder of, because I am dealing with a 2-dimensional flow, if I have a cylinder, one cross section of the cylinder I am considering. So if on the boundary of the cylinder z is equal to a e to the power I theta, my q becomes this. And if you remember that what happened in case of a uniform flow past a cylinder, when we have worked out, we have seen that on the boundary of the cylinder that q is equal to 2 u sin theta. Now again, what will happen, q when theta becomes plus minus pi by 2, then q will be 2 u plus minus 2 u. So whether it is in a, and that will show that the speed will be attaining, that means if I look at the speed, that will attain, rather I will put it, attain the maximum on the boundary of the cylinder, attain the maximum at theta is equal to plus minus pi by 2. Again, what will happen when theta is on the cylinder, because remember this is on the cylinder, because I am taking z is, because I am taking z is equal to a e to the power I theta. This is one of the point on the cylinder if the cylinder is of radius a. Now what will happen if theta is 0? If theta is 0, then I can easily see, because q is 2 u sin theta and 2 u into 0, that will give you 0. So the speed is 0, then theta is 0, and again at pi also we can see this is also 0. So that means on the surface of the cylinder, if I have a flow, and here if this is 0, at this point and this point I have no flow, whereas at this point and this point my flow is maximum. So that and again if you look at, because we have already seen our wz uz plus ua square by z. So again as z tends to infinity, we have seen that dw by dz is equal to u. and that shows that it is a uniform flow at far field. And if you look at this, so we can always say that the Wz given by this will represent the flow uniform flow past a cylinder. Past a cylinder of radius A. Another thing is here in from the application of Bernoulli's equation, if pi is the pressure at infinity, then P minus pi rho u square by 2 into 1 minus 4 sin square theta. Here this result we have derived in the by using the Bernoulli's equation when we did the application of the equation of motion. You can recall, this is a very important result. Now if I relate this one at theta is equal to 0, because at theta is equal to plus minus pi by 2, q is plus minus 2u, and what will happen here, theta is, if theta becomes plus minus pi by 2, then this will give me p minus pi, gives me, because this will be pi by 2 means this will be 1, so minus 3 u square by 2. On the other hand, when theta is equal to 0, that is theta is equal to plus minus pi by 2. So here we have seen that the speed is maximum, but p minus pi, we can easily see that this is one of the minimum. Again, when theta is equal to 0 and pi, we have seen q is equal to 0, but at that point what will happen to the pressure? So p minus pi, if theta is equal to 0, so this will give us rho u square by 2, because theta is 0 or pi, this will give us 0 and so on. So that means here, so this quantity will be one of the maximum. So what I want to say that when the, because we know that in a potential flow, when speed is maximum, pressure will be minimum at that same point. On the other hand, when speed is minimum, the pressure is maximum. So this is, we have one of our result we have already talked about. So we have seen that in case of a cylinder, that this is exactly what is happening, that the speed is maximum at these 2 points, and here at the same point the pressure is attaining the minimum. On the other hand, when the speed is attaining 0, that means at that same point pressure is maximum. So speed and pressure, they are interrelated, because from Bernoulli's equation we know that pressure head plus velocity head is constant when no body force is available. So that is what, and again we will not go to the details of the force calculation, because we have seen that we have the lift and drag force both are 0 in this case, and I am not going to again repeat the same thing. So this is another example, and here there are 2 flows, one is u a z, another is u a square by z. If you analyze the flow separately, w z is u z, this part will represent a flow, uniform flow, which is parallel to the x axis at a speed u, whereas u a square by z, if you analyze this flow, actually if there is the water is still water, the fluid is at rest, then u a square by z will represent as if a cylinder is of radius a is moving at a speed u in the fluid. So on the other hand, when you take the 2 fluids into velocity potential into account, you merge the 2 things together, then the flow is a flow past a uniform flow past a cylinder. So this is the difference between the 2. Now with this I will go to a another nice example where that will give us, that is in fact that is very important for the navigation channel. Often this is one of the very important problem in the olden days, particularly to path of, it will determine the path of a channel. So, suppose look at z is equal to e to the power w. This is a very interesting problem. E to the power w plus w, where z is equal to x plus I y and my w is equal to 5 plus I psi. So, how to go for it? We will do the same thing. I will put it, because when it comes to one of the interesting fact in complex function theory application, that always you can separate the real and imaginary parts, and afterwards we will try to simplify the problem. So, e to the w means e to the 5 plus I psi plus 5 plus I psi, and if you do that, that becomes 5 plus e to the power 5 plus I times psi plus e to the power psi. No, sorry, this will be e to the power 5 into cos psi plus I sin psi plus 5 plus I psi. And if we again simplify this, then our x will be 5 plus e to the power 5 cos psi, and our y becomes e to the power 5 sin psi plus psi. So, if I simplify further these two, my x minus 5 will be e to the power 5 cos psi. One has to be very little careful. Y minus psi will give me e to the power 5 sin psi. So, now what will happen here? Tan psi, if I divide it by 2, x minus 5 by y minus psi. A very interesting example, that is cos psi by sin psi. Then if you substitute for, and that I call this as then from this we can obtain easily y minus psi is equal to e to the power 5 sin psi e to the power 5 sin psi. Then we have y minus psi e to the power 5 cosine psi, and instead of phi I can call it e to the power x plus x rather. Let me do a little jugglery here. This part I will leave it here. I have x minus phi, so I always can get phi is equal to, from here I will get, can I get phi is equal to y minus psi by tan psi y minus psi tan psi. That is minus plus x, or I will call it phi is equal to x minus y minus psi by tan psi. I am telling you the algebra is a little complex here. Now, if I substitute for phi in this expression star. Substitute for phi in star, then what I will get, if I substitute here, I will get in star, then I will get y minus psi is equal to e to the power x minus y minus psi by tan psi into sin psi. So, now I have eliminated from this phi exactly, completely there is no phi in this. So, this is a function named psi. Now, if I say psi is equal to constant, if I say phi is equal to psi is equal to constant, then what I will get? Then I will get the streamlines. Psi is equal to constant will give me, will give the streamlines. That means this equation when psi is equal to constant will give me the streamline. So, if I can also write, if I say, that means I can always write y is equal to c plus e to the power x minus y minus c by tan c into sin c. So, that is the equation of the streamline for each constant. For each constant c, I will get a streamline. Now, in particular, if I put psi is equal to plus minus pi by 2, let us say psi is equal to, if psi is equal to plus pi by 2, what will happen? My y will be pi by 2 plus e to the power x, psi is pi by 2, psi is pi by 2, how much will be give me this quantity? That will give me 0, because and then I will get pi by 2 plus e to the power x. On the other hand, if I take psi is equal to minus pi by 2, then I will get y is minus pi by 2 minus e to the power x. Okay. So, that means now let me draw these two lines. This is a streamline, this is a streamline. If I draw this, you will see along the x y axis, if I draw it, let me say these are the lines, minus pi by 2, this is pi by 2, then what will happen, my flow, this will give a flow, and this will give me a flow like this. So, that means this is often called a paired entry into a long parallel channel. Why? Because if you look at this as the ocean, so this line, particularly this line, is a streamline. This line is also a streamline. If I look at the deep ocean, if these two lines are the streamlines, then there will not be any flow across this line. So, always I can say that if I use this as a channel for the navigational purpose, there will not be any flow across this. So, I can easily call this as a channel without putting any obstacle, breakwater or seawall or any kinds of things. I am able to make that there will not be any flow from this side to the channel, and in the process I can call this as a, I can use this for my navigational purpose, because this is the deep sea. When the ships will enter to the channel, then it can be easily used, because there will not be any disturbances from outside, and this area I can always utilize as my flow, because there will not be flow any along these lines. So that is why we call this as a paired entry into a long parallel channel. This is one of the very interesting problem, but one has to be very careful while working out this problem. Now I will go to a similar problem, which is of course a little different. So in the second problem, what I will do, I will look into again a problem of a channel which also can be represented as the flow. That one I will call it as if a convergent divergent channel. So what is this? Let us look at this function. Suppose I say z is equal to c cos hyperbolic w. So where z is equal to x plus I y. The problems are very interesting actually. C cos hyperbolic phi plus I psi, and now we have, if we expand this, this is equal to c cos hyperbolic phi. I will utilize the characteristics of this cos hyperbolic I psi plus c cos c sin hyperbolic phi into sin hyperbolic I psi, and this will give me, which implies this will give me c cos hyperbolic phi. Actually there will be a minus sign. Okay, so cos hyperbolic phi plus minus sign plus cos hyperbolic phi into cos psi plus c sin hyperbolic phi into sin psi. So which gives me x is equal to c cos hyperbolic phi into cos psi, and my y will give me c sin hyperbolic phi into sin psi, and from these two I can always get, if I say x by c cos hyperbolic phi equal to cos psi, and y by c sin hyperbolic phi, that will give me sin psi. If I say I utilize the property of the trigonometric function cos square psi plus sin square psi equal to 1, and that gives me x by c cos hyperbolic phi square plus y by c sin hyperbolic phi square equal to 1. So and this is, then if I put phi is equal to constant, which implies, because this becomes a constant, this becomes a constant, so that will give me ellipse. So my equipotentials are ellipse. These are my equipotentials. On the other hand, if I put the other way, like if I put my x by c, x by cos psi is equal to cos hyperbolic phi, and y by C sin psi as sin hyperbolic psi, sin hyperbolic phi, and I will utilize the property cos hyperbolic square phi minus sin hyperbolic square phi equal to 1. Then this will give me x by c cos psi, x square by c cos psi square plus y square, or rather minus y square by c sin psi square is equal to 1. Then I put psi is equal to constant. If psi is equal to constant, that means, and then I can call it x square by a square minus y square by b square equal to 1, where a is c cos psi and b is equal to c sin psi. Now what does this represents? These are the streamlines. For each constant c we will get a streamline, and these streamlines are nothing but hyperbolas. So I can call this, that is why it is often called as a convergent divergent channel. I can always fix my constant, and I can use, there is no flow along this, and then I use this as a channel, because this path I can always use this as a channel, and because of this often this we call this as a flow in a convergent divergent channel. I have a small error here in my previous. So if I go back to this one, there is a x square and there is a y square. This is the one of the error is here. So this can be easily corrected. Thank you. So this is the flow in a convergent divergent channel. See these two examples. In fact, when in olden days, when there was no way to calculate, hundreds of years back when the potential theory was being developed, and this complex function theory was used for analyzing various flow problems. In fact, these two problems has given us a very, even if in marine environment, to find a particular, to develop a navigation channel, people used to spend, because how to understand the flow characteristics, because once the understanding of the streamlines are clear, then one could understand, one we had a good understanding that there is no flow across a streamline, and that concept was used in many physical problems, particularly to understand the flow characteristics, or if there is a streamline. In fact, the streamline bodies, like if you look at an aircraft or a ship, they are all streamline bodies, and because if the ship becomes a streamline body, there is no fluid which will cross the streamline, and in the process we will have less load, because it will be flowing as if it is flowing along with the fluid, and there is it will behave as if there is a solid line. If you just, because along the streamlines we can consider this as a solid line, as if there is no flow which will cross this, and this concept was, in fact, it has helped in the design of several marine vehicles and also airborne vehicles. And even if today we always design a ship or a aircraft, all these structures are always streamline bodies. So the understanding of streamlines is very important when you look into problems related to aerodynamics or problems related to marine hydrodynamics. Now with this understanding, I have to go to two problems. As I have told that what will happen, I have already talked about source, I have already talked about the uniform flow and the flow past a cylinder. Now what will happen, because what will happen if there is a singularity in a flow, particularly let us look at a function wz which is of this form u into z plus a square by z plus m log Z minus Z naught. Because now if you look at this part, this is the uniform flow past a cylinder of radius A, and the speed of the uniform flow, the speed is u naught, whereas this is a source of strength M located at Z is equal to Z naught. Now what will happen, whether this flow will represent, when you add this, whether all the three characteristics will remain or not. Now if I look at if it has to be, suppose what will happen at Z is equal to R is equal to A. At R is equal to A, this Wz will not be a constant. What will happen to the stream? At R is equal to A, it can be easily seen that the stream function will not be a constant. Again, if you look at the dw by dz, and dw by dz will give us u0 plus or minus u0 a square by z plus m by z minus z naught. So when z is equal to 0, at z is equal to z naught, this will represent a source. On the other hand, at z is equal to 0, sorry, this should be dw by u square, this is z square. At the same time, when z is equal to 0, this will tend to, because z is 0 means this term will tend to infinity, and then this will not represent a flow source. Z will be at behaves like a source at z is equal to 0. And at, of course, at z is equal to z naught, this will again behave like a source. On the other hand, if I put z is equal to a e to the power I theta, z is equal to a, and z is equal to a dw by dz, u naught minus, this will give me minus u naught plus m by a minus z naught. So this is, because it has to be, then what will happen to dw by dz mod? Near a cylinder of radius a, because the speed will be 0 when at z is equal to a, but in this case dw by dz modulus will be m by a minus z naught, and this is not equal to 0. So that shows that this will not represent the individual flow characteristics. We suggest that because I have two things here, I have a source which behaves like a singularity. So if we have a singularity in the flow and we have a boundary, then the additive characteristics of the, I will say the additive property of the additivity of complex velocity potential will not hold good. Complex potential will not work out. That means, if I have two different flows, I cannot say that whether the combined flow will represent the individual flow patterns together. However, there are examples where you can say that this additivity will hold good, but this is an example where this additivity characteristics will not hold good. That is what I want to say. Now, I will take another example. Suppose I take W is equal to U z plus m1 log z plus m2 log z minus z naught. Here there is no cylinder, because as if I have sources, this is one source, this is one source, this is one source. Then what does it represent? So, we can always see, if I say my dw by dz, this will be give me u plus m1 by z plus m2 by z minus z naught. As mod z tends to infinity, as mod z will tend to infinity, dw by dz mod will tend to u. So, there is a uniform flow. It will represent a uniform flow, because at infinity the flow is uniform. Again, what will happen if I take, if I put z is equal to z naught plus r e to the power I theta, then where r is small, then I will get my dw by dz will give me u plus m1 by z naught plus r e to the power I theta plus m2 by r e to the power I theta. And again, if I take r tends to 0, that means my dw by dz, because this will be behaves like a source, this point only dw will z, because this will r tends to 0 means this will tend to r tends to 0. So, this will tend to infinity. So, dw by dz, once this is tends to infinity, this is also tends to infinity. Again, as r tends to infinity, and this term will tend to 0 and this term also will tend to 0, and in the process I will have dw by dz again will be u. So, I will have a uniform flow. In a similar way, I can also take, suppose I take z is equal to p naught r e to the power I theta, then I can easily say that I will my dw by dz again will be u plus m1 by p r e to the power I theta plus m2 by z p e to the power I theta, rather p, this is z is p into the not r minus z naught. And here again, when p is large, means again these two terms will tend to 0 and will have a uniform speed, whereas when p tends to 0, this will give us infinity, and again this will represent the motion of a source of strength m1. So, in the in fact, we analyze the three cases. In the first case, we have seen that we can have a uniform flow. In the second case, we have seen that the characteristics of a source of strength m2 located at z is equal to z naught, this characteristics also remains. And in the third case, we have taken as if a source of strength m1 is located at z is equal to 0, and the three characteristics of the flow, they are intact. So, the addition of the three flows does not affect the flow characteristics. So, in this case we can always say that the flow exists. On the other hand, in the previous example we have seen, because we have introduced a cylinder, and because of introducing the cylinder we have introduced a new boundary to the flow, and because of that the additive property was, it was impossible to ensure that the additive characteristics hold good. So, this is there are, so in general we can say that particularly when there is we all know that when there is no source and singularity, no source or sink in a flow, the flow will be regular. But the moment we have a flow, and if there are source and sink without any other boundaries, then we can say that any number of source we can add to the and it will remain, the characteristics of the source will remain, and we can individual flow characteristics will remain. On the other hand, if we introduce a boundary, then there is a chance that the flow characteristics will be disturbed, and this is and all these things are very clear from these two dimensional analysis of the flows. And again the complexity of the flow pattern is has been simplified, rather is simplified by introducing this complex function theory, particularly the complex velocity potential W. So, in the next class we will again introduce some of the more complex problems and understand how this complex function theory is helping us in solving more problems. Apart from that, we will then go to the conformal mapping, which is one of the very important mapping, particularly functional relationship, which will transform from a very, suppose we are in a very complex plane, from a very complex plane we can always transform this to a simple plane, and then analyze the flow in the simple plane and again go back to our original plane. So, where that conformal, that will come help us in solving again a class of problems. So, basically we can several two dimensional problems we can analyze by using the complex function theory, some of its application, and in the next couple of classes I will spend time on this complex function theory and analyze various flow patterns, particularly will emphasize on two dimensional flow, assuming that the similarity remains, flow characteristics will not be disturbed by such assumptions, and it has been also been verified from model test and even if observations that yes, we can assume for a large class of problem the two dimensional assumption is a valid assumption. With this I will remain today. Thank you.